Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 38 of our electrical machines subject. So this will be the last lecture of DC machines. After this we will start with induction machines. So today we will mainly discuss about two topics. First one is the starting of DC motors. Second one is the parallel operation of DC generators. So starting, okay, why is there a problem in starting? Okay, what is the problem? So starting, right, is bit difficult. So one, like take your example, the day when you started preparing for gate, that was a very difficult date because you were not accustomed to studying for constantly for 3 to 4 hours. But after the starting phase is gone, now you are on the intermediate phase. Now you are accustomed of sitting for 3 to 4 hours and studying from lectures and solving questions, right? So the starting phase is actually pretty difficult, as we have already discussed previously as well, that at starting, let's mainly we will be discussing about DC shunt machine. We will be slightly discussing about DC series machine as well. Okay, so starting, if I this series, sorry, if I see here that I know my speed will be, of course the machine is in rest, so speed is 0. If n is 0, there is no back EMF EV 0. We have discussed this multiple times. So the current IA starting, right, will simply be equals to Vt divided by Ra, and Ra is generally very low. Let's take few numbers. Let's assume that Vt is 200 volts. These are all considerable numbers, right? And let's say Ra is 0.5 ohms, right? If Vt is 200 volts, Ra is 0.5 ohms, then I can say what will be the starting current in this example. The starting current IA starting will be equals to Vt, that is 200 divided by Ra, that is 0.5. So this will be equals to 400 amperes. Okay, so this is the starting current. Basically this is the starting current. Now uh, what we can discuss is okay, so which is huge, right, which is huge. So how can I limit it? So the easiest way to limit is just adding a series resistance, right? If I added a series resistance instead of this, right, if I added a series resistance, then my IA starting will be Vt divided by Ra plus R external, and let's assume that the R external, right, or the starting resistance, let's assume it to be some uh, 25 ohms. If it is 25 ohms, then your IA dash starting roughly becomes 200 by 25, that is roughly it is 8 amperes. Okay, so it reduces drastically, right, reduces drastically. But there is a price to pay here. I cannot always keep this resistance connected in the circuit. Why? Because there will be a loss of IA whole square into R external, right, or R starting, right? I do not want that. Okay, I do not of course want that, right? Of course this was not in the plans, right? This was not in the plans. My machine is supposed to have only armature resistance, not R starting, right? So there will be constant losses here, right? Of course I do not want that. So what we can think of is, we can think of a mechanism, think of a mechanism with which with which we can connect the starting resistance initially then remove it after motor has reached to a certain speed. Right, basically if EB increases, then of course the motor will reach to a certain speed. After that, even if I remove the starting even if I remove the resistance, my IA will be the now VT minus EB, because EB will be the opposing voltage divided by RA. So now the current will not be that high. Okay, so this is what we want to do. Now, what are the drawbacks of high starting current? First of all, huge current will flow. There will be sparking in the commutators. There will be sparking in the commutators. Brushes will get deteriorated. Armature reaction will be huge. The current is higher, so there will be huge losses. So yeah, all these losses are there, right? So that's why we don't want this. So what we do, we want to gradually, like initially, the main aim is initially connect a large resistor then gradually reduce it. Okay, then gradually reduce it. That is the case that you have to understand. Okay, so gradually reduce it to 0. So there are few kinds of starter that we will discuss. This is the first kind of starter, that is the 3-point starter. So this is a 3-point starter. So why the 3-point, why the name 3-point? Because it has 3 points. That's why the name 3-point starter. Okay, sorry, my starting spelling here is wrong, right? Yeah, this has become starter. This is starter, right? Starting. So yeah, it is 3-point starter. So what we do is, like, we need to have an automatic mechanism, right? So initially when the machine is off, right, then this is my basically armature resistance, this is my series resistance that are connected in steps, and that is connected in series with the armature. So let's understand the working of the starter. So first of all, this coil is known as the holding coil. Why is this called as a holding coil? So initially, if everything is turned off, so this particular pointer will be in the off position. If I want to turn it on, what I will do, I will connect the supply and I will make this spring, like this is spring connected, make this pointer, connect this pointer to the point 1. Now if the pointer is connected to the point 1, what will be the direction of current flow? If I observe that this armature, like this, right, if I observe the direction of the current flow of the armature current, this will flow through here, come here, flow through all these resistors, come back through this pointer. This is actually, remember, this pointer is metal one, so current will flow through this pointer, it will come back here, follow through this overload release coil, it will energize the overload release coil and then come back to the line. Okay, that is the overall path of armature current. So what will happen is, as soon as I will turn it on, now what is the starting current? Now the starting current is actually quite different. So all for the armature current, all these resistors are in the path. So it is Vt divided by R1 plus R2 plus and so on, and it will go on, right? So basically now the starting current has been uh, managed, okay, it has been reduced. Now the important portion that comes is how can I like reduce this resistance. So if you see, this is known as the holding coil. Now we will understand why is this called as the holding coil. This is called as the holding coil because if you see, this holding coil is connected in series with the field winding, right? Field winding is connected here, right? It is connected here. So some Vt potential is getting applied across this field winding, and the same Vt potential is getting applied through this path, okay, through this resistor is returning here and through this path. So some sort of resistance is here in this path. So what will happen is that some current will flow through this holding coil, and if the holding coil, some current is flowing as it is connected in series with the holding coil. Because if you see, this one end is going here, okay, and the other end is coming here, okay. So basically what is happening, it is connected in, like, whatever there is in the current in the holding coil, same current will flow through here, okay, same current will flow through here through the holding coil, because you see same wire is connected. So it is connected in series with the holding coil, hence the holding coil is energized. If the holding coil is energized, this here I have a soft iron piece. So what will happen, it will produce a magnetic flux, it will attract the soft iron piece. Slowly the handle will move on the right hand side, so slowly the resistance will gradually reduce, because I'm moving from point 1, point 2, point 3. Slowly the resistance also will gradually reduce. That's it, okay. So at the steady state condition, this whole handle will come here, so no resistance will be connected, only the armature will be connected, right? Only the armature will be connected across the supply. So it is totally fine. So all of the working is fine. Now you might have a question, sir, this spring is there just for producing the restoring torque. So if anything goes wrong, automatically, if the holding coil is anywhere de-energized, automatically it will leave the holding coil, it will come here to the initial position, right? That's why this spring is there. Okay, we will see one by one the working. Now what is the reason for the overload coil? So this coil is known as the overload release coil. So this overload release coil, if you observe, it is connected in series with the armature, correct? This overload release coil is connected in series with the armature. Whatever current is flowing through the armature, it is connected in series. So for some reason, if there is some damage or something, right, if the armature current is going very high above a preset value, then this overload coil will be magnetized very high value, then this lever will be pulled up, okay, this lever will be pulled up. If this lever is pulled up, then what will happen, this is a copper piece, iron piece, what will happen, it will simply short circuit these 2 points. It will short circuit these 2 points. If it short circuit these 2 points, what happens, the voltage across the holding coil is short circuited, that means there is no voltage, that means the holding coil will be de-energized. If the holding coil is de-energized, simply it was keeping the pointer at this position, it will just simply not hold the pointer anymore, so it will release the pointer. Automatically the pointer will come back to position 1 due to spring force. So now again resistance will be there in the armature path because the current has gone above a preset value, okay. Now one more thing is that if let's say the supply voltage drops to a very low value, because basically the holding coil, right, is connected basically across the supply only mostly. So if the supply voltage for some reason drops below, so this shunt field terminals flux also drops very low value, so the current through the holding coil also drops, so then also it will release, because that is also a condition, abnormal condition, right? Maybe due to some fault or something, the supply voltage is dropped significantly. So these protection schemes are there, that if the supply voltage drops significantly, then also this holding coil will release the starter, and if the current goes above a preset value, then also this holding coil will release the pointer, okay, and it will go back to the high resistance state. So that is basically the working, okay. like that's it basically for the 3-point starter. I hope we don't need to explain much here. So the three key aspects of a DC motor whenever you are like you want to design a DC motor. First you have to understand how can I start the DC motor, how can I control the speed of the DC motor, how can I break the DC motor after it has reached to a certain speed. So speed control and braking already we have discussed. Today we are mainly discussing about starting. Okay, so why starting is required, all those things we have already discussed. So those things same KVL KCL they are just doing. Okay, drawbacks also we have already discussed. What are the drawbacks? You can go through this. Yeah, so how to limit, we will use the starting current starter, we will use a starter. Okay, so we will discuss about series motors as well. Now modern systems actually don't use this all starters and all, they use power electronics. So this is a mechanical kind of solution. So modern systems use power electronics, but of course the price increases. So we have DC to DC converters that can help control the starting current. Okay, so but traditional solution is using external armature resistance such as starter. So we have already discussed about that. So the working of starter is written over here. So mainly it is called 3-point starter because it has 3 points: line, armature and field winding. That's why it is called 3-point starter. What is the working principle? Working principle, the starter handle each begins at the off position. So we will begin our operation at the off position, and when moved to position 1 the large resistance is introduced, so the current is limited. Simultaneously the field current energizes the holding coil because it is connected in series with the holding coil. Field winding is connected in series with the holding coil, so gradually it will attract the iron piece, so the pointer will gradually move here. So this is actually called the stud. Okay, it is actually called the starter handle, stud, whatever you want to call. No, this is called the stud, these are called the studs, I guess. Yes, these are called the studs. Okay, so gradually what will happen, the resistance will be cut out, so resistance will gradually reduce. So holding coil connected in series with the field winding, when energized it holds the starter handle at the final position. Then we have no volt release. So if supply voltage drops significantly, this is also called as the no volt release coil. No volt release coil. So if supply voltage drops significantly, holding coil will be de-energized, the magnetic force drops and the spring puts it back into the off position. Okay, because there is some like weird condition, right, abnormal condition. Overload release, so if the like current is very high, then this overload release coil will be activated, so the magnetic trip mechanism shorts the holding coil as we discussed, right. It will simply short the holding coil, releasing the handle and disconnecting the motor to avoid the damage. Okay, so the advantage of a 3-point starter are the following: protection against the field failure. So if the field winding voltage is very low, then there is protection. Because why? Because if the field winding voltage is very low, then the IF will be very low, then the flux will be very low, then the speed will go abnormally high, right. So we don't want that abnormal high speed, so we need to have a provision, right. Overload protection, under overload the current through the motor increases very high value, so we have a provision to protect from overload. Now what is the disadvantage? Speed control above the base speed is not possible here, because if you remember, we also use a speed control mechanism where we intentionally reduce the flux. This is done intentionally, right. We intentionally reduce the flux to do speed control over base speed. But if I have a starter, then I will not be able to do it. If I have a 3-point starter, to be specific, I will not be able to do field flux speed control. Speed above base control is not possible. Okay, so because the magnet will become demagnetized and it will go back to off position. To resolve that, we have a starter named 4-point starter. Okay, so what is the advantage of a 4-point starter? So in case of 4-point starter, what happens is, instead of a single point, we have 4 points: line, armature, field, and each a separate point for the holding coil. Okay, so basically what happens this time, if you observe that our holding coil is supplied separately from the line itself. So if you see holding coil here, it is not connected with the field, it is directly supplied from the line. Okay, with a resistance is there, and it is directly connected across the line, I mean current is supplied through the line. So whatever field control I will do, because you can see I am changing the resistance here, it does not matter, it is independent of the line, it is independent of the field current, right? So my holding coil is independent of the field current, that is the only difference. Okay, so holding coil is supplied separately from the line, not in series with the field. So even if field current is reduced during speed control, holding coil remains energized, allowing wide and smooth speed variation above base speed. So even here, if the voltage reduces, this current also will reduce, right? Largely. So this current reduces, then also there is protection, there is under voltage protection, there is overload protection. This is same, this circuit will not change. So this is mainly used for the under voltage protection, this holding coil, right? This is also called as under voltage protection. So the disadvantage, if the field winding is accidentally open circuited, okay, the holding coil does not sense failure since it is not in series. So even if the field winding is accidentally open circuited, if the field flux is very low, then also our like holding coil will not sense anything, because we have separated the holding coil and the field winding. So there is chances of damage, right? As a result, the motor can run into dangerously high speed, posing risk of mechanical damage. Hence, no protection against field loss is provided. Okay, that is the thing about 4-point starter. You can go through the summary. Okay, so yeah, that was about the starter. What about series machine? So in series machine, just one thing you have to understand, that you cannot make your current go very high or very low, because like for in case of series machine, I know my field current is proportional to the armature current itself, right? So I cannot make my IA go very low or IA go very high. Both of these are detrimental. So what we do is, in case of series, right? This is, I am discussing about series and cumulative compound motors. So what we do is, we try to keep our armature current within a certain range, right? Because if I reduce my armature current very low, then my IF also will be very low. If IF is very low, then the flux is also very low. That is again detrimental. Again, I cannot increase IA very high, because of course copper loss, all those damages are there, that has been discussed. So in case of series, just you have to keep this in mind, that we will limit our current within a certain range, IA max and IA min. That is the limit that we will do for our armature current. Okay, that is the only thing that you have to keep in mind in case of series motors. So starting of DC series motor draw very high current at startup due to low resistance and zero back EMF. The large starting resistance is placed in series to limit the initial current. Resistance is cut out as the motor builds up. The starter includes both the overvoltage and no volt protection. It can be diverted as the resistance is cut. Can be diverted to the holding coil for sustaining magnetic holding. Okay. Uh, so if the resistance is cut, it can be diverted to the high holding coil. Yeah, basically the extra current will be diverted to the holding coil. And one just quick warning, that you should never start your DC series motor without mechanical load, because you know, initially, like if there is no rotation and if there is no load, right, it will produce initially IA will be very high. So the initial torque will be very high, right? Because torque is proportional to IA square, correct? So torque will be also very high. So there will not be any opposing torque. So motor like will rotate very fast initially. So that is why we never want to use our use our DC series motor at no load. Okay, that is during the starting. Now at no load, what happens? In no load meaning the armature current will be zero. It will not take up any armature current, right? So if armature current is zero, so my flux also will be very low, right? Very low. Then the speed also will be very high. So these are the two drawbacks. So we cannot use our DC series motor in no load, never recommended. That is what they have mentioned. And during starting as well, if no mechanical load is connected, torque will be huge, so it will rotate at a very fast rate. Okay, accelerate at a very fast rate that can damage the components of the machine. So these are the two drawbacks. Okay, so as I mentioned, we will limit our armature current between Ia max and Ia min. So a maximum allowable starting current and current just sufficient to prevent stalling. Basically, if I go below this, the motor will not start. Because why? Because I know the load torque will be greater than the developed torque. So if the load torque is greater than the developed torque, of course it will not be able to rotate correctly. Okay, so yeah, these are the differences. I hope you have understood this basic thing. So let's solve a very basic question, and then we will start the next topic, that is the parallel operation. So if I see over here a 230 volt 10 kilowatt DC shunt motor. Okay, I have a 230 volt 10 kilowatt DC shunt motor. It is to be started such that the armature current does not exceed twice of its rated value. So maximum value of the armature at starting should not exceed twice of its rated value. During startup, external resistance is added in series with armature, gradually removed in steps after the armature current drops to its rated value. Given that the field resistance is 115, so shunt resistance is 115 ohms. Total armature circuit resistance RA is 0.348 ohms. Neglecting the armature inductance, what should be the value of the external resistance connected in series at the time of starting? So at the time of starting, right, EB is 0 because speed is 0. So at the time of starting, what will be the armature current? Armature current will be basically VT upon RA plus the R series, R external that I have to connect, so that the maximum current at starting is 2 times the rated current. So what is the rated current value? Rated current value I don't know. So I can find out the rated current value, right? So my IA rated will be basically equals to, okay, do I know? Because at that point of time it will supply the rated power, right? So basically what is the IL rated? IL rated will be equals to P rated divided by VT, right? So it is equals to P rated is equals to 10 kilowatt divided by VT. VT is 230 volts. Okay, so this will be 1000 divided by 23, so 43.48 amperes. Okay, so that is the IL rated. But what is IA rated? IA rated will be, so what is the field current? It will be VT upon RSH. This time I will not assume IL rated to be equals to IA rated, because they have given me the information about the shunt resistance. If they wouldn't have given me the information about the shunt resistance, I would have assumed this to be my armature current. Okay, so I know there is a confusion when to assume this as an armature current or not. You will assume this as armature current if the shunt resistance is not given to you. Okay, this will be 230 divided by 115, so this will be 2 amperes. So from here I can find out what is my IA rated. IA rated will be equals to 2 minus this, so 41.43 amperes. So now I can easily solve this. Now this will be simpler. So this will be 2 times the IA rated, 41.43. VT is 230. So RA is 0.31 something, right? 0.348. 0.348. 0.348 plus R external equals to VT is 230 divided by 41.43. Okay, so this will be minus 2 into 230 divided by 2 minus 0.348. So your R external that you need to initially connect is the 2.432 2.42 ohms, 2.424 ohms. This is the initial value of external resistance that you need to connect. Now what are they asking? Now they are asking what should be the value of the first resistance. So this is the total resistance, right? So basically how many steps are there? Okay. So I have a starter, right? Let's assume this is R1, this is R2, this is R3, this is R4, right? So the starter will be in this position during starting, right? Because it will include all the resistance. So whole of this resistance, here the armature is there, I am not drawing it basically. So whole of this resistance together taken is the external resistance, that is R external is equals to R1 plus R2 plus R3 plus R4 is equals to 2.424 ohms. Okay. So what have they asked? What have they asked actually? What should be the value of the external resistance connected in series with the armature at starting? So this should be the value of the resistance, 2.424. Now next, what are they asking? What should be the value of the first resistance step to be removed when the armature current reaches its rated value? So if I am in this first state, they are telling me that in this state the armature current should reach its rated value. Okay, armature current should reach its rated value. So how will I find it out? So in the first state armature current, so basically what is the armature current in this case when it will reach here? It will be IA will be equals to VT minus EB divided by RA plus removing this resistance, all the other ones, right? Some, let's name it as R external dash. Okay, so I don't know what is my EB, right? So to resolve this, let's understand one more concept, last concept, I promise, last concept. After this only parallel operation is left. So one more concept we will learn. So actually what we do is, as I told you, that we limit our current between two ranges, IA maximum and IA minimum, right? So basically if I draw the circuit over here, right, circuit of the starter and so on, it goes on till the last point here. So the pointer, let's write this point as position 1, position 2, position 3, position 4. So this is 1, 2, 3, 4, goes on till here. This, let's say this is the position n minus 1 and this will be the position n. Okay, so in the first position all the resistance are in play. In the second position this R1 resistance is not in play, this R1 will go away. In the third position R2 will go away, R3 will go away, and so on. Here Rn will be here, right? Rn minus 1. Okay, and I have told you that our current must be limited between Ia max and Ia min. So when I am here in this position, pointer is here, what is the Ia maximum? What is the Ia maximum? So Ia maximum will be equals to Vt by this whole resistance. So let me write this whole resistance as, if it is at position 1, let me write the resistance value as capital R1. I'm ignoring RA for a second. Okay. So RA is very small. RA is small, right? That's why I'm ignoring RA. What will be the minimum value? So let's say I want to find out the minimum value. So because initially there will be some current, there will be some torque generated, the motor will rotate, so speed will increase, so the back EMF will increase. So I can say the IA minimum is equals to what, Vt minus whatever the speed it has increased to in the position 1 E1. This is the maximum value it will go to, then the value will become divided by R1. So this is the minimum value of IA, right? Because we want to limit our IA current as well, it should not go below a certain level, right? Now in the next step, when I am in the position 2, now what is the IMX? IMX now will be as soon as it reached the minimum position, I just switched my pointer to the position 2. So now the IA maximum will be, again it will be Vt minus E1, because of course as soon as it reached speed N1, I just moved my pointer to position 2. So speed will not change instantaneously, so the back EMF also will be same. So this back EMF also will be same, right? So this will be Vt minus E1 divided by R2. Okay, Vt minus E1 divided by R2. Now here what will be the minimum? Again same thing, right? IA minimum will be, it will increase its speed, it will be E2 minus R2. Again the same thing will happen. IA maximum in the third position, it will be Vt minus E2 divided by R3, and again here the IA minimum will be Vt minus E3 divided by R3. So one thing I notice, so I will go along. So in the last step, in this step, right, once my pointer will reach here, right? So in the last step, what will happen? In the last step, basically only RA will be left here, right? In the last step, basically IA maximum, this will be, let's say, Vt minus E n minus 1 divided by R n minus 1, correct? Not R n minus 1, sorry, R n, and IA minimum will be Vt minus En divided by small ra. So Rn only, Rn will be here, and in the last one, basically IA maximum will be basically Vt minus En divided by small ra, right? Because only this armature resistance will be present at the end. Here only armature resistance will be present. Okay, only n minus 1 is there. Okay. This will be, let me name it as n minus 1 only. Let me name it as n minus 1 only. Okay. Yes. Okay. This will become then n minus 2. Yeah, this will become n minus 1, n minus 1. So ultimately what you are observing is, if you observe the ratio of IA minimum upon IA maximum, so this Vt minus E1 will be cancelled. It will be basically R1 divided by R2. This ratio will be R1 divided by R2, right? So what do you observe? This ratio IA maximum upon IA minimum, if we observe here, it is IA maximum, here is Vt by minus E1 divided by R2, here it is Vt minus E1 divided by R1. So IA maximum upon IA minimum is what? R1 divided by R2. R1 divided by R2, or you can further write this, like it can go on, it can be written as R2 divided by R3, it can be written as R3, you can see the expressions, R3 divided by R4, it will go on. it will be equals to Rn divided by Rn minus 1 divided by Rn, Ra, right? Okay, that is what we have derived. So this is the expression that we get. Okay, so in our case, what we will use, we'll use the case because they have told me that what should be the value of the first resistance step to be removed when the armature current reaches its rated value. So in the first, if I am moving my handle, if I am moving my handle to the first step, right here, I'm moving my handle basically from the first step, I'm moving into the second step. That means I'm cutting R1 resistance, right? So my current has reached IA minimum at that point of time. So at that point of time, current has reached IA minimum, and the maximum value of current is this. So maximum value of current I already know. What is IA maximum? IA maximum value of current I already know. That IA maximum they have I know that it is 2 times I rated, and IA minimum they have told me as soon as I will move this to the second place, that is when the current reaches its rated value. So from the question, IA maximum is 2 times I rated, and IA minimum is IA rated, right? I can use this relation in this equation. So it will be IA maximum upon IA minimum. So it will be 2 IA rated upon IA rated equals to R1 upon R2. So it is R1 upon R2. So R2 is R1 by 2 basically. So how much resistance I need to remove? So previously all these resistance were there. Okay, this R1, R2, R3. So this whole was R1. Now as I am in the this position, then this is whole is R2, right? So R1 is the amount of resistance that I need to cut off. That is what they are asking, right? They are asking what should be the value of the first resistance in the step to be removed. So what is this value? This value will be basically small r1 value will be simply, as everything is in series, it will be R1 capital R1 minus R2. Very simple, right? So I know what is my capital R1. It is R1 only. I know what is my capital R2. It is R1 divided by 2. So R1 divided by 2 will be the resistance that I need to cut out. So basically R1 what is capital R1 that we had already found out in the previous attempt. Okay, a very difficult attempt, that is this one. This is my R1, right? So it is 2.424. So small r1 will be 2.424 divided by 2. Okay, this will be 1.212 ohms. Okay, so this will be the value of small r1. This is the amount of resistance that I need to cut out. So this is the answer for the part B. Okay, was a bit long, I'm sorry, but what can we do? It is what it is. Okay, so yeah, now let's move on to the next one, kind of a theoretical question. So here what have they told? They have told that why should a DC shunt motor not be stopped manually, forcing the starter handle to the off position? Why we should not force it to the off position manually? Okay, it causes heavy sparking at the all the studs as handle moves to off position. Maybe because if you see, right, if you see, if I bring back the starter, this is the 4-point starter. Let me, yeah. So basically, right, our working point of the starter is from position 1 till run position. We never put it in the off position. Why? Because let's say the motor is running, right? It is in the run position, and let's say I am in this position 2, this handle is in the position 2, and I take it to the off position. So if the motor is running, that means there is some armature current in the motor, and there is some inductance of the armature. And if I suddenly bring it to off position, that means it is open circuit, so current will be 0 amperes. So from IA current it went to 0 amperes. So there will be what? There will be a reactance voltage LA into del IL divided by dt, right? In no time, very small amount of time, the current will suddenly go to 0. Of course, inductance does not like the current suddenly going to 0, right? So it will produce a opposing voltage. So there will be sparking at the studs, because due to the voltage, right? Due to this reactance voltage, there will be sparking in the studs. Okay, that's why we don't bring it in off position. Let me read the other options as well, because this option is also there. It results in dangerous sparking in the final stud, which is absolutely correct. Same thing, right? Both are saying this kind of same thing only. It poses a risk to the operator due to intense sparking. Yeah, it will pose a risk. It will pose a risk, but of course, there is no option such as all of the above. So I will choose the option D, which tells me both option A and B will be correct. Okay. Now let's solve the next question. So in the next question, what happens if the field circuit of a DC shunt motor with a 3-point starter is accidentally broken while the motor is running in normal condition? So if the field circuit is accidentally broken, right? If the field circuit is accidentally broken, that means there will not be any current through the field circuit. So the holding coil will not be energized, right? If it is not energized, it will not hold the handle, so it will leave the handle. So the handle will go back to position 1. So the starter handle will return to off position. Yes, it will return to it will not return to off position, it will be returning to the 1 position. Basically it will be returning to the 1 position. So here there is no other option. So the motor speed will increase dangerously, but if the field coil is open, right, then we have a provision safety for a 3-point starter, that automatically it will go back here, right? Automatically the current will be very low, then motor will not go to dangerously high speed. So this is wrong. The armature draws excessively high current. No, resistance has been increased. How can it draw excessively high current? The motor will keep running without any issue. No. Motor will not keep running without issue, because of course the starter will go back. So basically it will go back to off position or the 0.1. Okay, specifically it will go to the 0.1 position. Okay, they have not mentioned here. So this was about the starting of DC machines. Now let's discuss about parallel operations. So first thing is bit of brief we have discussed about parallel operations, what can be the problems, circulating currents. So today we will clear all those things up and also solve a numerical. So parallel operation of DC generators. Why parallel operation is required? Same in case of generators. In case of transformers, in real world applications, single DC generator may not be sufficient to handle high load demands. So if a certain generator has a rated current of, let's say, 10 amperes only, right, but my load demands 40 amperes, how will I supply 40 amperes? So what we can do is we can basically connect 4 DC generators in parallel, which each will supply 10 amperes, okay, to share the load, improve system reliability. If one of the generator fails, there are other 3 generators which can supply some sort of current. If I have only one generator in the grid, if that generator fails, I don't have any backup. Enable maintenance of one unit without interrupting the supply. Operate generators efficiently at optimum load. So if I just use one generator, and if the rating of the generator is 10 amperes, and if the load also wants 10 amperes, then the generator is operating at rated condition, right? If I have 2 generators, then both the generators will share the load, so both of them will supply 5 amperes of current. So there will not be over excessive loading of generator. So not excessive loading. However, parallel operation is only successful when certain conditions are met. Same in case of transformer, right? We discussed. Same will be happening here as well. parallel operation will only be successful when certain conditions will be met, especially problem of circulating currents and load imbalance. So we will discuss these two cases. So first of all, we have to discuss what do I mean by drooping characteristics. So we know for a DC shunt generator that the terminal voltage is equals to Eg minus Ia Ra, and Eg is assumed to be constant if flux and speed both are constant, then Eg also will be constant. Okay, Eg is also known as the open circuit voltage, right? Open circuit voltage, because at open circuit there is no current, so or also known as the no load voltage, no load or open circuit voltage. Because if there is no current, there will not be any drop, then the terminal voltage will be simply this. So here we write this as Eg naught and this as okay, so this will be Eg1, this will be Eg2. Now you might see there is a bit of problem, right? This characteristics is known as the drooping characteristics. As the load will increase, this drop will increase, so Vt terminal voltage also will reduce, right? Now the thing is, this Ra resistance will not be same for both of the generators, right? The generator 1 may have a resistance of Ra1, the generator 2 may have a resistance of Ra2, right? Then they will not reduce by the same amount. For same increase of armature current, maybe the reduction in this Vt will not be same as the machine 2. Their slopes will be different. Who defines the slope? This Ra1. Because if you observe, if I find out the slope, it is change in voltage upon change in current, which is the unit of resistance. So this slope is given by Ra1 and this slope here is given by Ra2. So if their slopes are different, right, their operating points will be different, because if I am connecting two DC generators in parallel, the terminal voltage must be same, right? Vt must be constant. If Vt is constant and if this is Ra1, this is Ra2, right? So the current sharing will be different. Current sharing will be different basically, right? If here from here IL current is flowing out, so you can use the current division formula. So your Ia1 will supply basically IL into the opposite resistance Ra2 divided by Ra1 plus Ra2, right? Current division rule, right? So that is the difference over here. That is the difference over here. I hope you understood this point. Okay, so yeah, so their loads, they will share loads differently. So there is a problem regarding this, right? Load sharing is different. Okay, so there are few, like this is the one of the problems, right? They will share loads according to their resistance values. Got it? Okay. So basically, right, if you see that your Ia1 is this value, your Ia2 will be IL into Ra1 divided by Ra1 plus Ra2. So I1 divided by I2 is equals to Ra2 divided by Ra1. So they will share the load depending on whatever the resistance value is. So few conditions must be met, right? First of all, so if this terminal voltages are different, I mean of opposite polarity, then there will be huge circulating current. This we have discussed multiple times. I hope we don't need to discuss it again and again. So let's say if this voltage is Eg1 here in this direction, this is Ra1, and here the voltage is Eg2. So I hope you can understand what will be the problem here, right? Huge circulating current will be flowing. So of course their voltage polarity must match. Okay, terminal voltage must be matching. So this Vt must be matching. If this Vt is not matching, of course they will not work. Okay, and during loading also they should provide a common terminal voltage, and it's okay if their resistance are different, so they will share the load differently according to their resistance values, inversely proportional to their resistance values. Okay. Now, load shedding, already we have discussed how they will share the loads. So basically, IA1 upon IA2, already I have derived the formula, will be equals to RA2 upon RA1. Okay, just simply model each generator with a voltage source and that's it. Okay, now there might be a bit of problem due to some circulating currents. If there is some circulating currents flowing through the uh, motors, generators, right? So this problem arises in compound and series generators. If compound or series generators, a unique problem arises of circulating current. So if there is unequal current, right, which can cause runaway effect. Suppose one generator takes slightly more load. So let's assume that IA1 is greater than IA2. Then what will happen? Then if armature current is increasing, that means it is a compound generator or series generator. So the flux, right, phi AC also will increase. So overall flux also will increase. If overall flux increases, that in turn increases the EG, because speed is constant, EG increases. If EG increases, what happens? What is my what is my IA equals to? IA is equals to EG minus VT divided by RA, right? EG minus VT divided by RA. Very simple. If EG will increase, IO also will increase. So it's like a positive feedback. So this increases EMF further, causing it to supply even more current. This leads to a runaway condition where one generator ends up supplying almost the entire load while the other may even start acting as a motor. So other may take current. Okay. So this positive loop can severely damage the system. So what can we do to not damage it? So we can isolate the series windings. What we can do? We can connect this equalizer rings. This we have discussed like previously as well. How can I make the uh, voltages same? So we use equalizer. These are known as equalizer bars. You will say, sir, is the problem of circulating current finished? No, still there will be some circulating current if there is some potential difference here, but that circulating current will flow through here. That will not mess up the series field winding. So the series field winding flux remains constant or does not change, does not change. Hence we are able to prevent the problem of runaway. Okay, so that is the main crux behind this. So we will get a stable operation. Okay, they will not disturb the series field winding. So yeah, I hope you have understood this basic point. Let's do a question on this and then we will wrap up this topic. Okay, so this is the question. Two DC shunt generators are connected in parallel to supply a total current of 200 amperes. So if you have two DC generators, so let me write this equivalently. Let me write this as EG1 and this as RA1. RA2, EG2, and they are supplying a current of 200 amperes. So each generator has an armature resistance of 0.1. So basically both of them have equal resistance 0.1, and field resistance both of them has 100 ohms. So of course if they have field resistance, both of them will be in parallel. So don't forget the field resistance. So the field resistance will be in parallel here and here. So this is RSH, RSH. The no load EMF generated is 250 and 245 respectively. So here the no load EMF generated is, so EG1 is 250 volts, EG2 is 245 volts. Determine the common bus bar voltage and power output of each generator. So it takes say 200 ampere of current. Okay. Now we can apply KCL. Yeah, we can apply KCL, right? So if I apply KCL, the common voltage will be Vt. So let me assume this voltage to be Vt. So it will be Vt minus Eg1 divided by Ra1 plus Vt minus Eg2 divided by Ra2 plus Vt divided by Rsh plus Vt divided by Rsh equals to 200 ampere, because 200 ampere of load is going out. So I know all the values. I know all the values. So Vt just I don't know, except that I know all the values. Eg1 is 250. Ra is basically, all these are common denominator, right? So Ra is 0.1. So this plus Vt minus 245 divided by 0.1 plus 2 Vt divided by Rsh. Rsh is 100 ohms. So this is equals to 200. So this value will be basically 20 Vt plus Vt by 50, and this is equals to 2500, 2400. So basically 5000, sorry, 4950. 4950 plus 200, 5150. So from here I can calculate the common voltage. So this common voltage will be basically 20. So 1 divided by 50 plus 20 into 5150. So common voltage is approximately 257, right? If I'm okay, if I'm not mistaken. Okay, this is plus. Okay, one mistake I have done. All these are outgoing current. These are outgoing current. These are outgoing current. This also is outgoing current. Okay, sorry. All these are outgoing current, right? I'm assuming this to be outgoing, this to be outgoing. So this also should be outgoing here. This will be, sorry, I am applying KCL wrong. Okay. Machines पढ़ लिया, network सही से नहीं हो रहा. Okay, so this will be negative actually. So this will be negative value. So actually here this will be 4750. So 475. So 1 divided by 50 plus 20 into 4750. So the Vt comes out to be, so like it cannot go beyond 250 values, right? 250, because the no load voltage is 250. How can I go beyond 250? That was the like a sign that you had done some mistake. So 237.26 volts. Okay, this is my Vt value. And what are they asking? They are asking determine the common busbar voltage and power output of each generator. To find out the power output of each generator, let me find out IA1. So IA1 will be equals to this Eg1 minus Vt divided by Ra1. So Eg1 is 250 volts, right? Minus 237.26 divided by Ra1 0.1. So plus 250 divided by 0.1. So this is 127.37 amperes, quite a large value. Okay, so and what is the power delivered? So Pg1 will be what? It will be Eg1 into Ia1. So Eg1 is 50, so it is divided by 1000, it is 31.843 kilowatt. Okay, so that is what my EG value is equals to. So that is what my PG1 is equals to. Same you can apply for IA2. It will be EG2 minus VT divided by RA2. So like in this case, right, in this characteristics, we assume that the shunt is like not present, right? If shunt is present, right, then this will not be the correct analysis. Okay, so assumption is shunt field windings not present, or basically it is infinity, so R shunt is infinity, right? So that's why the analysis was that simpler. So this will be EG2, here this will be 245 minus IA1. So if I subtract IA1, this will be VT, so this will be 237.26 divided by 0.1, right, if I am not correct, yeah, 0.1. So here uh, what will be the power supplied? Yeah, this will be the power supplied, right? This will be the common voltage, yeah, this will be the current supplied. So this will be basically, here this will be 245 minus 237.26 divided by 0.1. So this current will be 77.4 amperes. So my PG2 EG2 into I2, so EG2 is 245 divided by 1000, so it will be roughly around 18.963 kilowatts. So am I doing anything? Okay, this current is very very small, 77.4 amperes of current. This current is very very small, and like I just want to recalculate if I have done everything correctly or not. So this is 250 minus, this is correct only, 237.26 into 10 into EG2, that is 250. Yes, it is correct, and here as well it is correct. Okay, so this will be the answer. Basically this will be the value of the power that each generator will supply. Okay, so yeah, I hope you have enjoyed this whole DC machines chapter. If you did, make sure to, like, again the same thing, make sure to comment down below, make sure to like the video. Okay, so these are the like attendance that I am expecting from you guys, and from next lecture onwards we will be covering induction machines. So we have covered everything, every single thing that can be asked from DC machines. We have not left any topic in DC machines. Okay, thank you for watching, and I will see you in the next lecture. Until then, happy learning.